in fact, it's nicely kind of reflected by a semantics of queries and responses with a notion of payoff, okay? And in that way, you can ensure that your programs, like your strategies, implement the type, okay? So in fact, yes. So fine, well, okay. I think I said enough about all this. So if we go back to the drinker formula, remember we started with this yesterday. Then I said, well, it's possible to kind of, take the formula as it is and interpret it as a formula of this tensorial logic. So it's more complicated, but it describes exactly what happens during the game, okay? And that's the whole point, okay? So you can think of it as some kind of abstraction of this, okay? And now, yes. And so it makes like a larger proof, but in fact, we don't care because this proof is immediately deduced from the proof, for instance, in the previous language, okay? But what is important here is that we have the knowledge of how many times we use each component. So in particular, if we look at the proof, we see the negations which correspond, if you remember, there is two first negation here, but really what is important is that they're just here to say that maybe I can come back to that point of interaction. So the contraction means backtracking. Now, right means I give a witness, then you give a witness, then I come back and I give your witness and we are done, okay? So in a way, this is the kind of trace of execution of the little strategy we played together yesterday, okay? And so typically, if you don't have the exponential at the beginning, the ability to backtrack, this formula is not valid in the logic, okay? So in a way, if you like, we are currently in the situation where we can put intuitionistic logic and classical logic in the same place, okay? This was already the purpose of linear logic, okay? So not a new thing, but the thing is linear logic was not exactly easily connected to the dynamics. Whereas here we have the game semantics, so we're pretty sure of what we're doing. And maybe I should mention that for the people who are interested. So there is a notion of polarity in logic, and in fact it's possible to kind of formulate the logic in so-called polarized way, so in a one-sided formulation. So really like a classical logic, if you like. But you should be careful that when you have a sequence like this, there should be only one formula which is called positive, okay? And in fact, this positive formula plays the role of the formula on the right, okay? So it's like putting all the context on the right instead of on the left. And then negations become kind of shift operators, and then the introduction of the tensor on the right is a conjunction, and introduction of the tensor on the left is a disjunction. And so we in fact reconstruct a logic which is just like linear logic, except that we need to be careful about polarities, and so we need to add these little shifts which enable typically to start from a positive formula and get a negative formula. Here a negative formula, you get a positive formula. Okay, but again, it's the same logic as before. It's just another formulation of the same thing. Okay, but so it kind of connects to what people call polarized logic. Okay. So now, okay. So what I will do is, in order to connect this logic to string diagrams, I need to come back a bit to categories and functors, okay? So I will show you, so I will spend the last 20 minutes introducing, you know already what is a category, but the notion of functor, okay? And a diagrammatic notation for functors, and the notion of natural transformation and the diagrammatic notation for natural transformations. So the diagrammatic I've chosen is, you will see, is kind of a natural extension of the string diagrams I've shown you, okay? And so if you like the notation, the purpose of the notation is to make it, I think, quite simple and accessible, and we will see how we can use this notion of functors and natural transformations to study the logic this afternoon. Okay, So remember that a category is a graph, okay, where you can compose arrows. So a kind of formal way to define it is just to say it's a class of objects, so the vertices. Between two objects, you have a set of morphism, of maps, of edges, and then you can compose them. So this means like you have the set of maps from B to C and the set of maps from A to B. You get a map from A to C. And here, for every object, you have a specific map from A to A. And then these two equations should be satisfied, associativity and the fact that F composed with the identity is equal to F, which is equal to identity composed to F. So this we saw already, but I wanted just to show you another way to write it down, okay? So now, what is a functor? Okay, so I said a category is a particular kind of graph, okay? So now, when you have two graphs, what do we do? Okay, well, we will take graph homomorphism, okay? What is a graph homomorphism? It's a function from the vertices of the first graph to the vertices of the second graph, and then whenever I have an edge between two vertices, I should have an image, and the image should be between the image of the vertices, okay? So the image of the source of the image should be the image of the source, and the target of the image should be the image of the target, okay? That's a graph homomorphism. Okay, so what is called a functor is exactly the same thing, okay? We take a graph and we transport it to another graph. The only thing we should be careful about is that the identity maps, okay, of the first graph are transported to the identity maps of the second graph. And when I compose two edges in my first graph, and I take the image of the composite, it should be the composite of the images. Okay? So this is what is written here. The image of the identity should be the identity of the image. And when I take F and G here, so imagine I have a map from A to B and a map from B to C. I take their image and I compose them. It should be the image of the composite. Okay? So essentially, it's a graph homomorphism which preserves the structure of a category. And the structure of a category is the ability to compose edges and the fact that on every vertex we have an identity. Okay. So it's really nice. I mean, something really nice with categories is that it's at the meeting point of order theory and essentially order theory and like algebra or monoids. Okay, so I will explain that. So a typical degenerate category is a partially ordered set. Okay, so when you have a partially ordered set, you do that always. Okay, you take the element of the ordered set, and so you define a graph where the vertices are the element of the set, and then you put an edge. Whenever x is less than y, you put an edge from x to y. Yes? And so this is a graph, and transitivity of the ordering relation means you can compose the edges. Okay? If x goes to y and y goes to z, well, x is less than y and y is less than z, thus there is a map from x to z. Okay? So in fact, you can think of a category where between two objects there is at most one map, okay, as a kind of partial order. Okay. In fact, very precisely, it's a partial pre-order. Okay, you may have kind of loops. Okay, but okay. So that means every order is a category, and so yes. So a natural question is, when I have two orders, what is a functor between them? Okay, because orders, you can think of them as categories. So what is a functor between two partial orders seen as categories? So I want to wake you up a bit. Some of you, not all of you. So yes, so the idea is really exactly that a functor, because it's a graph homomorphism, clearly it's a monotone function, okay? Because if x is less than y, then the image of x is less than the image of y, okay? Because it gives the structure of the graph, okay? Good? Now, second illustration, the first one is like a degenerate situation where between two objects there is, either one map or no map. So here, another degenerate situation, a category with one object, okay, one vertex. So who can tell me what is a graph with one vertex? You will tell me it's a graph with one vertex. But can you say more?
It has one edge.
Maybe more. So it's a, you see, thinking about a graph, yes, graph in the very liberal sense that you may have many edges between them. So one point and lots of edges. Not yet. A graph, I said. Yes, a graph. So a graph with one vertex is, yes, so it's like crossword in 3 letters, I should have said. 3 letters, yes, it's a set, okay? So now, yes, so a category with one object in 6 letters, 7 in French, yes. No? Monoid, yes, monoid, yes. So, so it's a monoid, and why? Because, of course, if a graph is a set, if a graph with one vertex is the set of edges, you can think of it just as a set of edges, okay? Then now you have the ability to compose the edges. So it's like a monoid. It's like a set where you can compose elements, okay? But in fact, I would say it's even nicer than a monoid in the representation because, you know, when we take multiplication, you know, when we multiply elements, we really are following a path, okay? Always coming back home, of course, but, well, still, it's more natural. Visually, it's more natural. Okay, so now, yes, the solution was on the board. So now, the question is, now when you have two monoids, what is the functor between them? Of course, when you think of the monoids as very specific categories. So remember, a functor is a graph homomorphism, but in that case, graph homomorphism doesn't say anything, really. It's just a function from the elements of the first monoid to the elements of the second monoid. But there is an additional requirement, which is that when you compose two elements of your monoid, so when you multiply them, the image of the multiplication, okay, of the composite, is the composite of the images. And so you have this property here. You know, the image of the multiplication, the composite of x and y, is just the composite of the images. And similarly, you have the identity, okay, is transported to the identity. So do you recognize this? Yes, maybe some of you, not necessarily all of you, but this is the natural notion of homomorphism between monoids. Okay? Yes? Is it something like, who knows about this, like monoids and homomorphisms? And okay, well, so what can I say? What can I say about this? Yes, so maybe the next example is good, yes. Because even if you don't like monoids, yes, you should know that an automaton is essentially a monoid. Okay, so in particular, every alphabet generates a free monoid, which is just defined like this. Okay, is a set of words on the alphabet, but it's not just. It's not just a set of words. It's a monoid because you can compose words by concatenation. Okay, and you can think of it as some kind of, yes, so now, okay, so there is sigma here. Sigma is simply, it's a Greek letter. Now I'm very careful. It's a Greek letter that says suspension, like suspension, okay? So suspension means you take a set and you suspend it and you get a graph, okay? So you add a dimension. A set, you can think of it as dimension 0, it's like points. And now when you suspend it, you have dimension 1. Every point becomes an edge, okay? So now, if you have a functor from this little thing to the category of sets, So we need to think about what this is, okay? So this category here has one vertex, okay? So a functor to set, what does it do? Yes. So you need to think about this little graph, okay? So it's a very simple graph. You have a point, and every word on the alphabet defines an edge. Okay, very simple, like this. No, so for instance, if we take our alphabet, you know, each of you, I mean, you take your name, we have a little map, like this, okay? Paul, P-A-U-L, yes? So now, we take this little thing, and we transport it into set. So what do we get? We get exactly the same picture, because it's really pictorial, okay, in set. So that means we have a set, and now every letter, there is a little function, okay, from the set to itself. Do you agree with me? Like, I started like this point and P-A-U-L, okay. Now I transport it here. I have a set and I have a function, like, because every map is a function called P, a function called A-U-L, okay. So it's a set equipped with a function for each letter. So what is it? You can think of it as a very kind of deterministic automaton, because every time you pick a state, so an element of that set, and a letter, you can jump to another state, which is just the image by this little function. So P, like, okay, yes. So that means that the notion of functor is kind of graph, if you like, it's a kind of graph homomorphism, but it's very expressive, yes. So now, when we have two functors, okay, so when we have two graph homomorphism, we could, or maybe I should, before speaking about transformation, maybe I should show you one way to look at these functors from a kind of diagrammatic point of view. It's a pretty ad hoc notation, but it's very useful, okay? Because I think it's kind of pedagogic if you want to think about it. So okay. So remember, we are building string diagrams, and in the string diagrams, a little f like this from A to B is a map from A to B. Okay. So now, what we call a functor is a way to transport a map from A to B to a map from f of A to f of B. Okay, in another category. So that means the image is here, okay? It's a map from f of A to f of B. And you can think of the white here, the white horizon here around, as the target category. So we are looking at the target category, and we're building a string diagram in the target category. So it's here. But now, it's quite natural to say that a natural notation for this is to kind of open a box, and you can think of it as a window. And this window here is inside, it's blue, and this is the color of the source category. So I will okay, so it's a little graphical device to kind of understand what these functors are about. So you have a category C. You transport it in the category D, and you have this map here is transported to a map here. Okay? So this map here is, okay, it's like this. This is the string diagram for the map. Okay? Now, we want to transport this map into this. So this means we want that, in a way, this map, which lives in this category, now is transported here, so it should live in this category. So it's quite natural to say, okay, let's construct some notion of box, okay? And this box, you know, a box is designed to connect two universes, okay? The universe outside of the box, and the universe inside the box, okay? So here, inside the box, it's C, and outside, it's D, okay? And you can think of really, this notion of image. Okay, we have a functor here, we have a map, and this is the image. Okay, so really we take it seriously, this idea of image. You see, we open a little like window, and so we're in D, but with this little window, we can look at the image of C. Okay, we'll look at so if you like, this box is a bit like a way for the, you have an eye here, and it watches inside the category C. Okay. So now, if we think about the definition of a functor, in fact, what are the two equations of the functor? The first one is, it says that if you take the image of f and g and compose the image, then it should be the image of the composite. Okay? And here, the image of the identity is the identity. So you have this equality. Okay? So this is a functor. And so now, this can be adapted to monoidal. So there's a notion of monoidal functor for monoidal categories. And I just want to mention that in that case, you have this kind of diagrams where you have several inputs and one output. You can go further in this way and have this kind of several inputs and sometimes several outputs diagrams, okay? And they are all kind of described by with this idea of two layers, okay? Two levels. There is the categories and then the boxes around them, which are functors. And for people who know a bit about linear logic, it's a way to understand the boxes, so-called boxes, exponential boxes of linear logic. But here I want to show you this notion of natural transformation, and then I will be done. So what is a natural transformation? Okay. So imagine you have two graph homomorphisms. Okay. So you have two from C to D. Then a natural question is it possible to relate them? So remember, when C and D are all partial orders, we said that functors between partial orders are monotone maps. So you know that between two monotone maps, there is a notion of ordering. You say this monotone map is less than this monotone map. So we want to lift this idea to categories, to generalize it to categories. So the idea is very naive, very simple. We said that a transformation from a functor to a functor is just a family of maps from the image. So you pick an object of the category A, and you want a map from f of A to g of A. So if you think about two monotone maps, we said that f is less than g, when for all x, f of x is less than g of x. Yes, you agree with me? So this means for all x, f of x is less than g of x. This means there is a map from f of x to g of x. Okay? But there is no choice here of map because the target category is an ordering. So there is no, it's a very degenerate situation. So if we want to generalize it to categories, we need to say not just that f is less than g, but how it is less than g. So that means for every object of the source category, we should have a map from f of A to g of A. Okay? So a transformation is good, but even better, there is this notion of natural transformation. So you see, it has to do with degrees of freedom. Okay? So when you transport a graph into a graph in two different ways, then you can transform one homomorphism and one graph morphism into another graph morphism. But this is one degree of freedom provided by the target category. Yes? But there is another degree of freedom provided by the source category because you have all the edges in the source category. So the transformation is natural when the two degrees of freedom match. Okay? So that means you take f of A and you map it to g of A. So this is in the target category. But now you say, OK, I will also play a bit with A. I will map A into B in the source category. And we ask that this diagram commutes. Okay? And this is what is called a natural transformation. And so pictorially, this is this thing. Okay? So a natural transformation is something like this. You have a functor here. You have the little f. And then the natural transformation in the target category. This is a map from f of A to g of B. And the equation is that that the square I've shown you, it says that this little thing is equal to this one. Okay, and this, what is important is this looks like little stupid diagrammatics, but it's everywhere in mathematics. Okay, these transformations. When we find one, it's like a gem. Okay, we keep it and yes, and so we have these versions. So for the people who like for instance linear logic or these situations, we have a variant of natural transformation in the monoidal case, and in that case the theta, because there are several inputs and one output, when the theta meets the box, it's duplicated because you need the theta for each of the inputs. Okay, yes?
In these diagrams, what object is there to be indexed on?
Theta here, you mean?
Yes.
So theta is indexed by B.
Okay.
So it's like exactly like when you take two monotone maps, okay? When you say for all x, f of x is less than g of x, in a way the relationship is indexed by x.
And on the right-hand side, is it indexed by A?
Yes, but here it will be indexed by B, and here A1, AK. Yes, because it's a map from f of B to g of B, and here a map from f of A1 to g of A1. Okay, so you see these kind of pictures in my case emerge from looking at linear logic and proofness and trying to understand it from a purely string diagram way. Okay, so what we will do is we'll use this kind of language, so this afternoon, so that we can look at the kind of category of proofs, okay? So typically a category of games and strategies, and we study it, and then we realize that it has all the structures that defines a logic, and the logic will be tensorial logic, and then from that, so it's a bit like in the case of a monoid, you see? You look at a structure and you realize it's a monoid. So you may look at the free monoid, okay? So given an alphabet, take the free monoid. So we'll take the free, so what I call dialogue category, and we see that it's a category of games and strategies, but all the definitions are very elementary. The constructions can be complicated, but all the definitions are very basic. And so the idea is to start from really basic ideas like this symmetry between me and you when we interact logically, and from that, the tensor product and so on, and from that reconstruct the logic. Okay, and this is possible thanks to these tools like string diagrams and so on, and I will speak about this afternoon. Thanks. So are there questions? Yes, because that seems to be the ritual. No, I think you've had enough of it. So thank you, yes. Break? No? Are you?